let's say that we have two charges separated by 6 centimeter distance. This charge is 0.00000, well, I think I lost track of zeros, 1/1,000,000th of a coulomb, or a microcoulomb. There are 5 zeros and a 1. 5 zeros and a 1 here, a microcoulomb here. So we have two 1 microcoulomb charges separated by 6 centimeters. Now the magnitude of the force, which is just going to be written F, is just going to be, in this case, K Q1 Q2 over R squared. To be careful, I should have absolute value signs around this. So let's do that. And these absolute value signs, again, simply indicate that if these charges happen to be opposite, and this came out negative, the force, the F, is still the magnitude of the force, and that's still going to be positive. That's why we need the absolute value signs here. Okay, anyhow, if we do this calculation, it's very straightforward. We plug this charge in for Q1, this charge in for Q2, and the 6 centimeters for R. And of course, we express the 6 centimeters in meters because the units of K, which we write here, okay, this is K, the 9 times 10 to the 9th Newton meter squared per coulomb squared. The units of K contain meters. So we want the units of R to contain meters. We don't want to try to cancel centimeters squared with meters squared. Of course, we write the charges in coulombs because we have coulombs here. When we do this calculation, again, it's very straightforward. You can plug in the numbers. I believe that we end up with 2.5 newtons. Now, you should actually do that. I do these calculations in my head, ask my students in class to correct me if I happen to be wrong, and I am fairly often. And I'm not particularly concerned about whether that's accurate or not. You put in the numbers and determine whether that's accurate, and if it's wrong, correct it. Okay, so anyhow, we see that at a 6 centimeter separation, about this far apart, a microcoulomb charge and a microcoulomb charge here will have a force of repulsion of 2.5 newtons. Now, 2.5 newtons is a lot more force than we observed for these tape strips. Okay? The forces that we observed for tape strips, we believe, were on the order of a few thousandths or even a few 10,000ths of a newton. Okay, from the deflection of the tape hanging as a pendulum and the weight of the tape, as we illustrated at the beginning of this session, we determined the force of attraction to be something like 0.003 newtons at a typical 6 centimeter distance. Now, if we assume that both charges are equal, the charges, in other words, are equal and opposite, we want to determine what charges it would take to give us 0.003 Newton force at a 6 centimeter distance. We could figure this out by proportionality. This is about 1/10,000th of the 2.5 newtons, actually about 1,000th of the 2.5 newtons that we got for the 1 microcoulomb charge. The square root of 1,000's 30, and that would indicate that if the charges were equal, we had about 1/30th of that microcoulomb. And that proportionality argument would give us a quick estimate of what we should get. But if we don't know that, and if we don't have a point of reference, we can assume that Q1 equals Q2, write F equals K Q1 Q2 over R squared, and we should probably, again, put the absolute value signs there. It doesn't make a difference for this calculation, but it's good form to do that. If we let Q equal Q1 equal Q2, just let Q stand for the common charge, then Q1 Q2 becomes Q squared. So we have K Q squared over R squared. Now if F equals K Q squared over R squared, we can easily calculate, or we can easily solve for Q. We get Q as the square root of FR squared over K. We can put the numbers in, and we calculate Q to be about 3.5 times 10 to the negative 8th coulombs, which is about 1/30th of a microcoulomb. you divide 30 into 10 to the negative 6th, you get about 3 times 10 to the negative 8th. So this is consistent with our previous calculation. Now what this tells us is that the charges on these pieces of tape are probably on the order of a few times 10 to the negative 8th coulombs, a few hundred millionths of a coulomb. Now that would be 3.5 millionths, or 35 billionths if you prefer, or 0.035 millionths, 0.035 microcoulombs. This is the order of the charges in any case that we apparently have on these pieces of tape.